So please share your screen.
So we saw in the last lecture the explicit derivation of the ground state wave function. We wrote the wave function using Bethe answers. So this was meant to complement previous information given in the course of Balázs-Potykai. So as you understand, the world of integrable models is very wide, fascinating, and useful to interpret the experiment. We will come back on this point later in the course. So I would like just to give a few further information to give at least a certain minimum panorama of things that you can do. So Balázs didn't mention the thermodynamic part of finite temperature, and he focused on the integrability issue and on the algebraic structure of the Bethe answer. So let me give really a minimal information on what you do at finite temperature at equilibrium. So therefore, let me talk about thermodynamic Bethe answers. So this was introduced in a paper by Yang. And this is a Journal of Mathematical Physics, 1969. So I really would like to mean as this introduction just an invitation to read this paper, because it's a very nice paper, really beautiful. You will enjoy for sure reading. So now I will switch for this reason to the notation of the Yang original paper, and I will write the Bethe equation in this form: Kj 2 pi ij over L plus 1 over L sum over L from 1 to n theta Kj minus Kl. So just a notational matter with the lecture of yesterday. The theta of the lecture of yesterday was minus this theta of Yang, but this is not the problem, but just to alert you. And also I wrote 2 kjl over 2 pi in terms of nj minus n plus 1 divided by 2. But this gives rise to this expression once that the I1, In, if you take the notes of the lecture of yesterday, this will be minus n minus 1 divided by 2 minus n minus 1 divided by 2 plus 1, and in step of 1 arrived to n minus 1 by 2. So if you remind, the integer nj that we were introducing yesterday were such that this is valid both for n even. In that case, the ij are half odd, or for n odd. In that case, they are integer numbers. Okay. So, and I also remind kj minus k, I defined as 1 over L. Yesterday I was calling F, today I call rho, just to make you ready to read the Yang paper. Okay, this was F of the lecture of yesterday. And the integral equation was an equation for F, so therefore we have an equation for rho. So this is the ground state, t equals 0. So now the point of the Yang construction of the Bethe answers equation at finite temperature is to observe that you could have other i's. So you could have minus n plus 1 divided by 2, minus n plus 3 divided by 2, going in this direction. or you could have n plus 1 divided by 2, n plus 3 divided by 2, and so on. So since these are not occupied at the final temperature, they are not used in the Bethe equation, since these are the i's that you have to insert here to have the case related corresponding to the ground state, I call this holes. This is very natural because as we commented, and also Bolash commented extensively, these are like fermions. So you occupy certain and you don't occupy other, like fermions, in which for the Pauli principle you cannot occupy two levels. Okay, so at this point, let me introduce the notation that L rho k dk, that's the number of particles. So in the interval k plus k. Okay, while I call L rho tilde k dk is the number of holes in k plus dk. So it is clear why we wanted to write rho tilde, because at finite temperature, the thermal fluctuation will make possible the occupation of the holes. So to do this, let's introduce a quantity f. So again, not the f of yesterday, but the f of the Young paper, and also of, for example, the book by Bainok and Shamai. So you have a quantity, I don't know if you can see up to here, I start here, 2 pi L fk equal to Lk minus sum over theta k minus kl, L from 1 to n. And it is clear that L fkj is equal to the ij when j is going from 1 to n. While when it's a certain I tilde, not different from that, it will be another quantum number. So now I introduce the quantity of all and particle, rho k plus rho tilde of k. And this is number of particles and holes in k plus k. So now you see that this is using this expression is L f of k plus dk minus f of k. So is dfk. So therefore we can write so we can write 2 pi fk equal is rho k plus rho tilde k is equal to f prime k, where the prime is the derivative with respect to prime.
Andrea, can you lower the
lower this way?
so we can see the
Okay. 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 Thank you. So now I can write the equation for f. The equation for f is 2 pi f k minus integral from minus infinity to infinity dk prime theta k minus k prime dk prime. Now you understand that this is valid not only for the Lieb-Liniger, but in general, as soon as that you put the correct theta, and so therefore that you use the appropriate S matrix. So you can write, trying to not be wrong with the prefactor 2 pi is 1 over 2 pi minus integral dk prime from minus infinite to infinite theta k minus k prime over 2 pi rho k prime. Okay, the rho is related to the density n. I don't write the 1D because it's clear that it's 1D. Integral from minus infinite to infinite dk rho k. And of course, this was what also Bolash wrote for the Heisenberg models. And there you have, this is related to the magnetization. The energy, the density of energy, E over L, is integral over dk k square ok. Okay, so now it arrives the main point of the construction, which in the Yang paper is done in a seemingly effortless way, very simple. So when you go through the paper and you read the paper, you could say, how could else you should have done? Okay, so please read it because I have personally that impression reading that test, that feeling. So now Yang say, let's stay at equilibrium. So beta equal 1 over k dt. And then let's minimize the free energy, not the energy. So to construct the energy, so you have it once that you have rho, but you have to calculate the free energy. So you have to calculate also the entropy. So you have to calculate how many are the k's admissible in the region k plus k and k plus the k. So for a given rho and rho theta, the total number of admissible k of k's is L rho of k plus rho tilde of k in the k. But now you have to distribute your case in holes and particles. So the number of possible choices is L rho k plus rho tilde k in dk factorial divided by L rho k dk and L rho tilde of k dk factorial. So now, since this is only between k and k plus dk, this defines the variation of the entropy, ds.
Excuse me.
Yes.
I'm sorry, can you explain again the argument for writing the entropy?
The argument to write?
The entropy, the one that you
yes.
just did.
So we defined a certain number rho, the particles, and a certain number of rho tilde, the holes. So when I consider an interval k and k plus k, I have a total of rho plus rho tilde. This is a total number. But then I have to distribute this total number of k in particles and holes. So when you distribute a series of objects in two subclasses, you write the factorial of the total, one and the other. So this is the total, the number of possible choices in which you can distribute your solution of the better question in particles and holes. Okay, so total, particle, holes, and these are the number of choices because it's the total factorial, the factorial of the subclass of particle and subclass of holes. Okay, so that's if you wanted the definition of the entropy. Once that you understand that the number of ways in which you can construct your states, that after you will have to determine by minimization of the free energy. Once that you understand that what you are distributing to create the states are the quantum number itself. Okay, the quantum numbers themselves.
Okay, thank you.
Okay, so now we have to do ds. Now I need to do the log of this ratio. I don't write here. I don't write any longer. It's the same as before. Now, using the Stirling formula, it becomes L rho plus rho tilde log rho plus rho tilde minus rho log rho minus rho tilde log rho tilde. And if you remind the entropy of fermions, this is the typical form. And here you see that you have the sum of the two with the log minus each two, exactly as you have for fermions. So therefore, if I define the entropy per unit length, this will be the integral of decay, this quantity, rho plus rho tilde. I don't write the dependence. I don't write the dependence on K, log rho plus tilde minus rho log rho minus rho tilde log rho tilde. Okay, so now we are ready to write the Gibbs free energy. So I do the density G. Now this is a function of G rho tilde. So now we passed the difficult point, if you want. So now you have just to calculate the G, and you have to do the minimization of the DG, and then we'll give the equation, the TBI equation. Okay, so this will be 1 over L E. You have to put minus the chemical potential to fix at the end N. I think that at T equals 0, we were implicitly doing integrating between a minus capital K and capital K of yesterday. Okay, but final temperature, you have all the K possibly occupied. You have to fix explicitly the mu as you do for Fermi gases, minus 1 over beta S. Okay, so now this becomes small e, because I remind that now I'm putting e divided by L, S, capital S divided by N, and I also defining, S divided by L and N divided by L. So this is E minus mu N minus S divided by beta. So this will be integral from minus infinite and infinite K squared minus mu rho and minus 1 over beta log of rho plus rho tilde, sorry, rho plus rho tilde log of rho plus rho plus rho tilde minus rho log rho minus rho tilde log rho tilde. Everything integrated in the K. Okay, this is my Gibbs free energy. Now I want to find, since I'm interested to the equilibrium, I want to find the distribution for the equilibrium. I want to, for the equilibrium of the particles density and the holes density. So I needed to do delta G rho equal rho equilibrium. That's what I want to find. And rho tilde equilibrium equal to 0. Okay, now it's a matter of doing this calculation. I will sketch, but please redo it because these are just the derivative of this. So in order to simplify the notation, I write the equation rho k plus rho tilde of k. This is 1 over 2 pi minus integral dk prime theta k minus k prime divided by 2 pi rho k prime. And this let me write as 1 over 2 pi minus a certain operator which I call G applied to rho. It's an integral operator. And the kernel is just theta. Okay, so from this you get that delta rho tilde is equal to minus identity plus J delta rho. And then we want to do because 1 over 2 pi doesn't have variation. Okay, and by doing the derivative of the G that I have here, no, I just erased, sorry. So I have delta rho beta k squared minus mu, because this was in the integral, plus delta rho tilde log of rho equilibrium plus rho tilde equilibrium divided by rho equilibrium, plus delta rho sorry, this is delta rho, this is delta rho tilde log of rho equilibrium plus rho tilde equilibrium divided by rho tilde equilibrium equal to 0. Now I substitute this relation between delta rho and delta rho tilde, you simplify, and then you get, by doing just the simplification, rho L n rho equilibrium by rho equilibrium, tilde and non tilde, minus G log rho equilibrium plus rho tilde equilibrium divided by rho equilibrium. And eventually we write this as 1 plus rho tilde divided by rho plus b beta k square mu minus k square, if I'm not wrong with the sign. Okay. G is the operator. It's an integral operator. Okay, now I define rho tilde equilibrium divided by rho equilibrium. And I call this epsilon k. So then you substitute, and then you get beta epsilon k minus G, the log of 1 plus E2 minus beta epsilon k equal beta square k beta k square minus mu. Okay, so now this is a compact expression. This is a compact expression for using the integral representation, but if I want to write the equation in full glory, this is k squared minus mu equal epsilon k minus 1 over beta integral from minus infinite and infinite, so this is kbt, dk prime, theta of k minus k prime, that for the Lieb-Liniger is minus 2c over c squared plus k squared, log of 1 minus e2 minus beta epsilon k. Now you have to solve for epsilon k, and this will be n integral dk rho equilibrium of k. Okay? Once that the epsilon k are known, since rho plus rho tilde is equal to 1 over 2 pi minus g rho, so, and the rho tilde is rho e to beta epsilon k, then I have the third equation relating rho equilibrium of k 1 plus e beta ek 1 over 2 pi equal to, so I like well, 1 over 2 pi minus integral dk prime theta k minus k prime minus infinite and infinite rho equilibrium of k. So these are the equations. Sorry, let me erase these are just the definition. So when you have this complicated integral equation, so you have to start from a guess, suppose for epsilon k. You have to write what you don't know equal to all the rest. So, for example, you can start from guessing, for example, you could do in other ways. You can fix epsilon k. Now epsilon k is fixed. Now you guess, then you solve this again from equilibrium rho, and then you calculate finally epsilon k, you calculate the mu, then you have the epsilon, and you see if you get the initial guess. If not, you reinsert here and you go on. Okay, so this ends the equation of the TBA equation. And again, I suggest you give a look really to these young papers, because so you see a really clear crystalline approach to this equilibrium of finite temperature. Okay, so on this point I don't want to go on, because I should show that for t equal to 0 you retrieve the previous formula. They do. They satisfy all the limit. For example, in the Tonk-Girardot limit, you get the result for the Fermi energy at finite temperature of the 1D Fermi gas. You do, and for your, according to your different problem, you use this equation with the appropriate theta. Okay, this was an information that I think is useful also because, as you can imagine, experiments are done at finite temperature, and there is a paper. The 2009 PRL, which is called the Yang Thermodynamics on an Atom Chip, or a similar title. I think Jerome last week gave the reference, in which they compare for the truly one-dimensional model of one-dimensional ultra-cold Bose gas. They compare with this thermodynamics, finding agreement. Of course, you have to consider that you have a parabola. So before that you do the comparison, there is a little bit of work more, but these are the questions, and I wanted to give you this information. Okay, so this was a point that I wanted to clarify. Another point that I would like to show you is what use you can do for of the solution of the Lieb-Liniger integral equation. Yesterday we said that if you know epsilon gamma, so you know the energy, then you calculate the sound, the pressure, the equation of states. Now I would like to give a very simple a very simple use that you can do of epsilon gamma that we studied yesterday, and one reason to study really epsilon gamma, so to have it with high precision. So let's come back now to t equals 0. And let me remind that, as I discussed, the mean field equation for the condensate wave function, with all the discussion that we did that there is no condensate, but if it is mesoscopic, gamma is small, then you may consider to compare this with the experiment. So you have d psi over dx equal minus, now I restore the units, d square over dx square psi plus u 1d psi square psi. As I tried to comment, if I don't, so this psi is a function, not an operator, and the integral from minus infinity to infinity in dx of psi square is equal to 1. Now, this is the classical nonlinear Schrödinger, and this is the classical counterpart of the quantum nonlinear Schrödinger, which is our beloved Lieb-Liniger model. In the full quantum version of the problem, you have psi hat, that will be a function of x and t. This is an operator. You write in Heisenberg representation, you have this equation, but now instead of having a psi square, you have psi hat dagger, psi hat. Okay, just the operator. Okay, this is the classical nonlinear, but can we do better? So, in a sense, this failed badly when I increase gamma, because if I calculated the energy, the ground state energy of this classical nonlinear Schrödinger, you don't get the right energy. Let me remind you what is the energy. So the energy, so now I will write psi square equal to rho. Okay? This is what in the previous lecture we called n1d. So, but in nonlinear Schrödinger notation, usually you call the density rho. So the energy associated to the nonlinear Schrödinger equation is integral over dx psi star minus h bar over 2m psi, and then you have a plus u 1d divided by 2 psi to the 4. Okay, why there is this factor 2? So please, you know, but let me repeat because now it will arrive in a moment. So you want that this is the energy. So suppose that you have an external potential, you will have a plus b psi. That would be the energy of your problem. So you want that psi and psi star are canonically conjugate variable. So you want that dE over d psi star is equal to I h bar psi dot. And it is, because when you get the functional variation with respect to psi star, you get minus h bar square over 2m d square dx square psi. But now I have to do as well the derivative u1t over 2, the derivative with respect to psi star of psi to the 4. Psi to the 4 is psi, let's write here, psi to the 4 is psi star psi square, and is psi star psi, let me write it this way. So when I do the derivative with respect to psi star, I get 2 psi star the 2 simplify, and then I get psi star psi, which is exactly this. So I have a factor 2 here. So super obvious, but just to remind one thing that everybody knows. Okay, now let's go to calculate the equilibrium energy. So the equilibrium energy will have psi equal constant, and this will be just the square root of the density. But now, if I calculate the energy, I get rho square times the length times U1D, which is clearly not the Lieb-Liniger energy. Okay, so one way to improve this classical formalism is to say, okay, now let me change the non-linear part, and let me write a certain function f of rho psi that's arbitrary, but at least I can impose that the energy is the same of the Lieb-Liniger. So I choose f in a way that the energy is that we calculated. Okay? So I pretend in this approach, that the energy such that psi and psi star are canonically conjugate variable, when I calculate at equilibrium the ground state for homogeneous psi, translational invariant psi, is the Lieb-Liniger, but we know who is the Lieb-Liniger energy. The Lieb-Liniger energy is h bar squared over 2m times density. Let me write the density n over L square, what I was calling N1D in the previous lecture, times n times E gamma. Who is gamma? Gamma is C divided by the density itself. Okay? Now, the game that I want to play with you is the following. I want to choose the F in a way that the energy is the Lieb-Liniger one. So therefore, it is clear that it cannot be any longer psi to the 4 rho square. Has to be something related to the Lieb-Liniger ground state energy, and in particular of epsilon gamma. Okay? So
Are we assuming the constant?
not necessarily. So I'm going. So this is the Lieb-Liniger of the ground state. This is the energy that I pretend that give all the dynamics, which is a constant of motion of this equation. Okay? So therefore, I have to put a certain g of rho, Now you have to find g of rho such that this is the correct constant of motion. So there should be a relation between g and f. And I also wanted to pretend that the energy of the ground state is equal to that. Now let's go, what is the energy of the ground state? Now it's clear that psi has to be rho, there is no derivative, and that would be energy of the ground state of this putative equation would be L, that would be L times G rho. What G is not yet fixed, but now, since Lieb-Liniger has truly this energy, because we calculated We wrote the Lieb-Liniger integral equation. We solved, we discussed with this E gamma. Now you identify the two for the ground state. Okay. Now it is clear that when I insert this G, that's only chosen in a way to reproduce the exact energy. It is not guaranteeing that the mean field dynamics of this equation give 1 point quantities in agreement with the full quantum dynamics, but it's for sure much better than the mean field. And also, you can expect that when you study collective oscillation near the equilibrium, this gives a reasonable result. For example, if you use this equation and you calculate breathing oscillation, you get a very reasonable agreement with the experiments without using quantum dynamics of the Lieb-Liniger. The point is that since the G or the E is the exact one, if you stay nearby, you are reasonably good. It's clear that if you go far from the constant, from the equilibrium, you are bad. But for collective excitation, that's reasonable. Okay, so this gives the relation between G and epsilon, and you find that G of rho is equal to h bar squared over 2m n 1d, which is rho cube E gamma. Okay, so if I know epsilon gamma, I have a certain density, I know it's G in this equation. Now the question for you is you have to tell me who is F such that this is the correct energy at any time. Okay, so who is F of rho? So let me write here. Who is F of rho in terms of rho? So this is the question before the break. Again, I remind that if you solve, if you have a proposal for the solution, I want the H bar, the M, the 2 and the 3 correct. So in order to be, you want to show me? Yeah. No, non è quella ancora. So Guido is close. So let me remind the answer given to me. So far I had 2 Guido, 3 Jacopo, 1 Francois, 1 Francesco. So please. Allora, mi si chiede di rispondere, di ripetere. So, I was asked to repeat the question. So the question is, I know who is G rho, I know who is the energy, I ask you to tell me who is F as a function of rho, such that when I solve the problem and I have psi of x and t, psi star of x and t, and I compute the energy is this, is conserved, is a constant of motion. Okay, I have an answer. No, both Federico and Carlo wrote the same, but is this not correct? Okay, so h bar over 2m rho square 3e. No, I think there is yeah, so Jacob did correct. So f of rho is equal to, so the point is that you in order that this is the energy should be dg over d. So let me write correctly. So dg over d psi star, in order that they are canonically conjugate, should be equal to f of rho psi. Because I want that when I derivate g on psi star, I get exactly this. So, but then I can do dg over d rho over d psi star. This is just psi. So you have to do the derivative with respect to rho. But when you derivate with respect to rho, you have to derivate this, but you have to derivate also gamma. Because gamma is C over rho. That's the point. So the answer that I received, they didn't derivate this. So when you do the derivative of both, you get f of rho equal h bar over 2m 3 rho square e gamma minus gamma rho square dE over d gamma. So therefore, if I know gamma dE over d gamma, I know the nonlinear term that I have to add there. So now it's a bit painful that you don't have an analytic solution, because if you want to study this, you do the Runge-Kutta or other numerical methods to solve this equation, but for each time, you have to solve the integral equation, which is very heavy numerically. So you have to parameterize your E gamma, you get calculate rho in position x, because you promote rho as a x and t. And then if you have an efficient parameterization of the E gamma and the E over D gamma without solving the integral equation, you gain a lot of energy. Okay, so this was an example in which the knowledge of the E gamma, it's very important. Now, for example, I can calculate breathing mode. So breathing mode, for example, if I have a potential like this, it will be in the ground state. I remove a little bit, so I open. This will start to oscillate like this, and you want to calculate the omega breathing as a function of rho. For example, you can do by using this f of rho. It's a paper of Olshani, PRL 2013. It's a good agreement with experiments. Okay. Okay. So, questions? If not, we take a little bit of break.
Okay, maybe we can take a break.
Okay,
for,
10 minutes.
10 minutes.
Okay.
So probably we restart, no?
Okay. So therefore, let me briefly motivate the second part. So both the course of Bolash and mine, which are related, talking about beta ansatz, Lieb-Liniger, and the intertwined, I hope that showed the beauty of the mathematical theory of these integrable many-body systems. And we emphasized, and I tried also to emphasize that they are related to a physical system in which you do experiment. So with the help of Rob Shah, which is in the audience, now I would like that you see also the physical part of the story. So how an experiment is done and what you can measure, what you can do. So just to have a feeling of how this beautiful mathematical structure as a counterpart in concrete, in real experiments. So let me introduce very briefly Rob. Rob is finishing his PhD in the University of Sussex. He works as experimentalist there and works with Peter Kruger and Tom Barrett. Tom, I think, is in the audience. I just answered to him. So I thank you very much, Rob, for the help. And please, Rob, share your screen and show us some experimental.
Thanks, Andrea. Yeah, so Andrea's pretty much summed up.
You have to come closer if you can to the
microphone,
please.
Can you hear me better now?
Yeah, now it's better.
Okay. As Andrea said, yeah, rightly introduced, that's kind of what I'm going to be talking about today.
Sorry, the audio is not good, so probably you should.
One sec. Let me just try to
go as much close as you can to the microphone, or I'm sorry, I think it would be useful if you can go closer to the microphone.
Yeah, let me just try and change my microphone settings.
Yeah.
Is that any better?
No, it's the same. I think you have to go closer.
Oh God. Is it better now?
Yeah, this is a bit better. Yeah.
A bit better. Okay.
Yeah,
I apologize about the audio.
No problem.
Oh, 1 second. Prop it up. So, sorry about that.
A little bit better now, yes.
I remove my video, and
okay. So can everyone see the screen?
Yeah, we can see.
Okay, good. Yeah, so the experimental system I'm going to be talking about is on an atom chip, which I'll explain as we go. And it's a nice tool to do kind of 1D gases here, which relates to this Lieb-Liniger model well. So the group that we're in is Andrea said Peter Kruger is our group leader, and we're based in Brighton. So for those who don't know, this is where we are in relation to the rest of Europe. And this is a picture of us in front of our lab. So I'm going to show you what the lab kind of looks like, some of the main components of it, but I won't go into too much detail, just to give you an idea. Then I'll talk in a bit more detail about what an atom chip is and how we create these trapping potentials, and what the important parameters are, how they relate to these Lieb-Liniger parameters. Then I'll show you like how we detect our atoms and what information you can actually get out of it. Then I'm going to talk a bit about first and second order correlation function and the phase coherence, and show a bit about condensates and quasi-condensates and what an experimental images kind of look like. And then hopefully at the end of it, we can try and run the experiment in real time, and you guys can try and create some of your own clouds. If it works, though, you never know. Okay, so this is the lab. So we work with rubidium atoms, and you have to trap them in a vacuum chamber. So you have something that looks like in the top right here. So I've noted this is the science chamber. So this is where the atoms are. And inside this chamber, we have this atom chip, which is a microfabricated planar structure, which has like a series of micron level wires on. And you can pass current through them and make trapping potentials, which I'll talk in the next slide. Yeah, and it gets quite messy. Once you start adding everything in, it's quite a complicated system. I don't know if anyone's seen this kind of setup before, but yeah, you need for your laser cooling, so you need lots of optics and light, and we have a pre-cooling system, and you need fancy cameras, and you need lots of electrical connections for everything inside, and so you have this mess at the end. But let's ignore that for now, and so we'll talk about the atom chip a bit more and how we make a potential, because this is like one of the most important part of what your gas will be at the end, is determined by this potential that you make. So we do magnetic trapping. Other experiments can also do optical potentials and stuff, so I'm just going to talk about the magnetic trapping. So this is going to be quite basic, and some of you may probably already know this, so but for those who maybe don't, then hopefully it's interesting. So it's quite simple. In practice, you use the Biot-Savart law and also the right-hand rule. So if we take a single wire, we have current flowing in one direction, you can figure out which way the magnetic field is pointing. And we then apply a bias field in an opposing direction, and this will cancel out the field from the wire at a certain height above the wire, so like this, and you get a minimum in the center, and that creates our main trapping region. And then the only problem is that's trapped along X and Z, and I'll call this the perpendicular direction in the following slides. And then it's not trapped along Y yet, so the longitudinal direction or axial confinement. And so to create that trap, we have what we call two leg wires, send current through them, and you get magnetic field potential that looks something like this. So they're both harmonic at the bottom, but in the radial direction you have a much higher trapping frequency, which we call the omega, and that lends itself to making these high aspect ratio traps, and it's ideal for these 1D things because you can make it very thin and long. Some important points about these fields for later is that we have a trap bottom which is defined by these leg wires. It's important that this is non-zero because we have polarized atoms in the MF equals 2 state. But if your minimum...
Rob, can you please remind to the audience who is MF?
MF is the magnetic quantum number the electronic state. So it's a Zeeman level.
Okay.
So yeah, that can be positive or negative. And so if you have a negative MF state, your potential has a minus sign in front of, and instead of you getting a potential minimum, you have a potential maximum. So if they mix, if you get -2 MF atoms in there, they won't be trapped. And that's a problem if you get close to 0, because they start becoming degenerate in the mix, and they can have what's called Majorana spin flip losses. So it's important that's not 0. That is also, but it's also important in determining, sorry, this slide's not skipping. There we go. Your trap frequencies here. So the lower the trap bottom is, we can get a tighter radial confinement, and so you have a payoff between those two. Obviously, you need atoms left, but this relates to our Lieb-Liniger parameters, the interaction thing, dimension with quantity gamma. So you want to, so if you want to increase this, then you want to really be playing with omega perp. So that's the C really. If you want to minimize your density, the important trap frequency is omega y, longitudinal confinement here.
Sorry, just you are rewriting the main expression. Let me rewrite at the blackboard so that everybody can make contact with the previous lecture. Just a moment. I will put my video. I hope that you can see my video. Okay, so we said several times, but let me connect with the Rob slide. So the three-dimensional constant we call the U3D is 4 pi h bar square A3D divided by m, and this is entering in the potential between the particle in 3D. So in 3D, you have that the potential is U3D times delta of R x minus y. This is the potential. And you have E3D of rubidium, for example. Then we go to U1D, which is the one in front of sum over delta xi minus xj in the Lieb-Liniger. Okay? And this U1D is U3D divided by 2 pi L per square. So, okay, this is the coefficient of the delta. And U1D is h bar square over mc. And therefore you get the formula C2A3D divided by L per square that Rob just wrote. Okay, so C, U1D, U3D. So these are the three numbers. And therefore gamma finally is simply this C divided by the density. So, and Rob reminded these two formulas. A last point is that we call the lambda equal omega perp divided by omega in the direction of the Lieb-Liniger. I think Rob is putting along y. So I think it should be omega perp divided by omega y.
Yeah, that's correct. Yeah, I'm sorry for the mixing of coordinates, but this is how our atom chip, we originally labeled them, so it's just easier for me to keep that the same. I'll go back to sharing.
So can you remind, you can take back the screen.
Yeah.
Can you remind what lambda you can do?
What range of lambda you can get?
Yes. So you can vary lambda.
Yeah.
How much for the audience?
So you can go to very low aspect ratios. It's a bit tricky due to the way that the atom chip is set up, but you can get to less than 10, but you can go to very high aspect ratios a lot easier, and you can get up to plus 100, even much higher. If you have a good quality atom chip, you can get very close to the Y. You can get a very high omega perp, and that's really where you control the aspect ratio. Well, it's the easiest way to do it.
And can you repeat? You said, but please re-say what you have to change in your setup to change lambda. So the ratio between omega perp and omega y. So
first I'll go individually. How do you change each trapping frequency? But obviously it depends on both. But so omega perp depends on how close it is to the wire and what the offset field is here. And so what defines how close it is to the wire is how much current you put through the wire, and the field it produces, and the opposing X-bias field that you apply. So the closer you get, the tighter that omega perp will become. I also here in this plot, I've kind of tried to show what happens when you apply the anti-Yoffie field, which I've just shown in the previous slide. So this controls what the trap bottom is. If you apply an anti-Yoffie field, or this is the BY bias, you start cancelling out the field that comes from these leg wires, and you start pulling the trap bottom down, and that also makes omega perp tighter. So you have two different ways to control omega perp. For omega Y, the main thing is the current that goes through the legs. And so if you want to make it tighter, you increase the current going through it. And when you're close to the wire, the dependency of the trap bottom goes with the distance from the surface. There's actually a turning point, so when you're far away, it's 1 over delta Z instead, but don't worry about that for now.
Okay, so varying the current, for example, I leg, you vary omega Y.
Yeah.
And varying omega perp, as you said, you change L perp, because L perp is square root of H bar divided by M omega perp. So when omega perp become larger, L perp become smaller, and the C become larger, and the gamma become smaller and become larger, correct?
Correct,
So
yeah.
You control the Lieb-Liniger parameter in practice.
Yeah, that's how you want to go about it. And also the other parameter control is temperature. And just, I won't go into lots of detail, but you use radio frequency evaporation, which basically you set a final frequency, and that kind of kicks out all the atoms that were sitting high in the potential, which are hot atoms. So you kick out your hot atoms, and the final radio frequency sets the final temperature of the cloud. Also the 1D parameters that get talked about a lot is the chemical potential compared to H bar omega perp and KBT H bar omega perp. And if they're both less than the H bar omega perp, that means that there can't be excitations to higher states, and this is where you freeze out the transverse excitations.
Can you tell a typical number for H omega perp divided by mu?
So if you want to, in our experiments, for example, we can get down to mu over H bar omega perp to 0.5, and it's very easy to go a lot higher than that. You can get up to 10 or something. So you can go what you call very 3D. In terms of KBT over H bar omega perp, it's a lot harder to get very cold to make this smaller, so get that less than 1. And we can get to 1 or 2. The reason why it's harder is kind of more technical problems, where you need to have a good quality vacuum so you can perform your cooling more efficiently. So as you cool, you actually kick out more atoms. But if you can't cool very efficiently, you kick out more atoms than you want to. So when you try to get very cold, you actually have very little atoms left. So that is definitely possible to do, but it's tricky. So sometimes they say this is the chemical 1D parameter and this is the thermally 1D parameter. And just say a bit more about the Lieb-Liniger parameters and how they relate to what kind of gas you might want to make. This phase diagram, which is quite common. You guys will have maybe seen it before, but basically if you can tune your interaction parameter, and also they have this dimensionless temperature parameter, and you can control kind of what final system you have. So they have this very strongly interacting regime, which we talked about, and which is the Tonks gas, and we have the quasi condensate regime and everything else. So you look more into that if you're interested, but that's kind of roughly motivation of why you want to control these things.
So sorry, just back. First, to avoid any misunderstanding in the audience, I remind that the lines in this figure are just a guide for the ice. There are no transition. It's not happening that a gamma equal 1, you do a transition. No, it's just to say that you pass from a regime to another regime, okay? So just to avoid that people misunderstand this figure. And second, can you put the mouse, can you put your pointer where you are in a typical experiment?
Yeah, well, actually, that I don't quite know, but I would say that we're
no, I think below. No, you are.
Yeah, we're somewhere. We're around here.
Yeah. Okay.
Isn't the dashed area a typical experiment?
It was in 2009 when this review was done. Yeah, so it's closer to the typical experimental area that was accessible, let's say, when this plot was done.
So you're asking about experiments now?
Yeah, I'm telling the experiment that Rob is going to show.
Okay.
So now I have to do this. I already said several times, but with cold atoms, there are many ways in which many setup that you can have. For example, you can have optical lattices. You can try to make gamma larger by confinement induced resonance. You can choose a different setup. So Rob is talking about a particular setup in which he has the atom chip, which is an advantage for some purposes. But I think there is not easy to put the lattices. So any scheme has advantages and disadvantages. But for example, you can explore the region which is below the dashed cigar in this picture. Is somehow order of gamma, if I will remember, 10 to minus 3, 10 to minus 2, maybe 10 to minus 3, and T, let's say order of 1. So it's below the dashed area in this plot that was done in 2009, and the dashed was representing typical values in that moment, let's say. Okay, go on, please.
Yeah, so I'm talking about atom chips, and the other common way in these systems is to use optical traps, but they, like Andrea was saying, they create lattices, so you have a lot of gases in one go. So you try and image that, you have an average over many. Whereas in an atom chip, you can just create one cloud at a time, and so you can get single cloud properties, which is one reason why you might want to use an atom chip. And if you are wanting to test some of any of your theoretical models, then if you want to look at single cloud properties, then you probably want to look at an atom chip experiment for help.
Yeah, so let me repeat for the students, just to be sure that everything is clear. So let me do the video. So as I mentioned, can you see my video? Yes. So I mentioned this in the first lecture, but I think it's useful to remind here. If you have a lattice like this created by two counter-propagating laser beam, two pairs of counter-propagating laser beam, here you have this structure, and then you have many cigar in this direction, in the perpendicular direction. So if you want to study single trap cigar, that's not good, But if you want to have a large gamma, this is better. So you understand the different realization may have different purposes, let's say. Okay. So Rob is showing a single trap, single cigar, if you want.
Yeah.
Okay.
So now I'll just tell you how we actually detect the atoms.
Yeah.
So this is probably the most common way of atom detection is this absorption imaging, and I think a lot of you probably know or have heard about it. But the setup is basically we have our atoms trapped on the atom chip. But then to image them, what we do is we turn the trap off. So it kind of freezes the properties, and we let it fall with gravity, where we can take a picture of it. And the reason we do that is in trap it's quite complicated to image in situ. So people do it, but it's complicated for a few reasons. One, you have very high densities, and which becomes a problem because you can fully absorb all the light before it gets through the whole of the cloud. You have spatially varying magnetic fields, which changes the absorption cross-section of the light as it goes through. So it's so most people do imaging after time of flight, and you shine like a resident probe light once it falls and after it's expanded, and you get a shadow image on your camera, and we convert this into optical density, and that is related to your atom density with this formula here. This lambda here is the frequency of the probe light, not the aspect ratio as we were talking about briefly. So this basically means all we can do is count atoms at whatever their location is. That is the detection method. You also want to know, if you're going to relate what you detect to what you wanted to see in trap, is that you have to know how it expands. So you can see here that the aspect of the cloud has changed quite a lot, because in trap you have a long cigar shape, but it actually kind of flips around during time of flight, because you have the very strong interaction energy radially, which converts into kinetic energy as it falls, and so you have a very big expansion radially. So you'll see BEC images looking like this, even though in trap they're actually it's much longer in the this is our y direction here than it is in our perpendicular direction.
So can you remind what are typical at time of flight?
So this particular image is taken at 34 milliseconds time of flight.
34 milliseconds, okay.
And people range it anywhere between 5 and 34 usually. I mean, you can look at very early time of flight. It depends on what you want to do, but it's if you're doing very early time of flight, you can be quite close to your atom chip still, and that can be difficult because you can get diffraction coming off the atom chip, and the cloud can be still very dense. So people usually have a longer time of flight for that reason. It's also worth noting that the resolution is now diffraction limited, so you can't see features that are really, really small. So good experiments have a resolution of a few microns. So if you want to look for features smaller than that, you're going to have to try and find a group that have got very, very good imaging. So that's important to be aware of. People do have very fancy imaging systems. They're just difficult to make. For example, our resolution is about 5 microns, 5-6 microns. What else have I got here?
So can you remind, Rob, can you remind after 30 milliseconds how large become the red area that you are plotting? So just to give a feeling.
I will, so in the next image I'll show that a bit more. The final point here is that it's a destructive method. So you make one cloud, you take a picture of it, and then the cloud's destroyed. So if you want to take more data, you have to keep making clouds repeatedly. And just to say that there are other imaging techniques which are non-destructive, but again, they're less common. So if you want a non-destructive imaging, then you have to make sure that that group has it. So next here is a bit how we extract our data. So we have to do a fit to it. And as Andrea was asking, it's just actually the sizes of the cloud after it expands. So this R here is the Thomas Fermi radius in their respective directions. So the what should we call it? The radial size of the cloud is. Sorry, I've labeled this slightly wrong. This should be, instead of R, it should be 2 times R. So R is the radius and not the full width. So the perpendicular direction here would be 2 times 210 microns. So it's 400 microns. So it's very big. And in trap, it was it's usually around 1 micron or less. So it's big expansion. This particular trap has a large thermal fraction, so that you can see we have a fit. You have a Gaussian shape on your thermal cloud, whereas the condensate has a inverse parabolic, and that comes because you can apply the Thomas Fermi approximation on these clouds, which I think you know, but then the ground state is parabolic, and that's why the condensate matches, has this parabolic shape. So you can separate out what the thermal fraction and the condensate is, and that's quite useful for when you want to determine the temperature, because you can fit to the wings of that and figure out how much it's expanded, and that's how you work out your temperature. And if you have a very pure condensate and you can't see the thermal fraction, it becomes quite tricky to measure the temperature. There are methods there, but yeah, they are.
This temperature should be nanokelvin, right?
Yes, it should be. I'm sorry if that's
nano Kelvin. Yes.
Yeah, I've made a mistake there. Yeah, and has anyone got any questions so far? Yeah. Okay. So this is what I'd call a BC. So, and so I go into the next bit of my talk. I'm going to talk about how we move away from BCs and we start going into these quasi-condensate, these 1D clouds. I'm going to talk about the first and second order correlation function, and how we can measure that. So the first order correlation function is describes like the phase coherence of the cloud, which is something you can't directly measure, but there's the way around it that comes from the time of flight expansion, which is interesting, is that these phase correlations in trap actually turn into density fluctuations at the time of flight, and this comes from this the velocity is proportional to the gradient of the phase, and this means that if you have a cloud where the phase is fluctuating, you will see density ripples after time of flight, and this comes from this first order correlation function, and there's an important parameter here, which is the phase coherence length. So this is the exponential decay constant. So that tells you how the distance scale at which the phase in this gas is correlated. And as you can, I've got an example for a BC and a quasi-condensate. The BCs display what we call long order coherence, and the phase coherence length is much larger, or larger than the size of the cloud, and the phase very slowly varies across, or doesn't. It should be constant. If it's a true BEC, it doesn't vary at all. When you, sorry,
Rob, sorry, just to remind one theoretical fact. Tomorrow we will come back on this point. So when you have the one-dimensional pure system and you stay at t equals 0, Lieb-Liniger, and you calculate the correlation function, G1 or similar, they decay at power law at t equals 0. But also in the one-dimensional theory, if you go to finite temperature, they decay exponentially. Indeed, you see the temperature in this formula. Okay, tomorrow we will talk about this, but go on. So just to comment about this difference between finite temperature and the zero temperature, even in the one-dimensional Lieb-Liniger pure case.
Yeah. And just to say as well, what the this phase coherence length as well, you have your temperature and your density go into this as well. So you can control your phase coherence with this parameter. And it's random. You can see this is a GIF of about 50 images in a phase fluctuating cloud. And you see the fringes is in different positions the whole time. So if you take a mean of that, you actually get a smooth profile. And here I have a BC, and you can see that there are no phase fluctuations, which is nice. So how can I measure, what was we call it? Our correlation function now. So we can't actually measure G1, but we can measure G2, so there's density correlations after time of flight, which relates to G1. And because, well, so in trap the density fluctuations are suppressed. So what you see after time of flight is only coming from the phase fluctuations. So this is a nice way of looking at what the phase correlations are in quasi-condensates. And so this is the experimental process of how we make this measurement. Is because you have these random fluctuations, you need to take lots of images. We take about 250 images, and from that I can calculate the mean. And then take the difference between the mean and the single shot, and you get a residual, which just shows you the fluctuations in atoms over the envelope. And from that, you can look at G2 by doing this autocorrelation, self-correlation function on each of the residuals, and you can take a mean. The way this G2 is known as G2 tilde, so it's normalized by the mean profile. So what you can see here is that you have something varying above and below 1. And this means when it's above 1, you're more likely to find an atom at this position delta to Y. That's what we call bunching. And when it's less than 1, it's anti-bunching. So you're not likely to find an atom there. When it's 1, you are neither likely or not likely to do it. So they are not correlated in that sense with respect to this mean. And you can also look at this in frequency space. So one thing we're looking at is the power spectrum of these density ripples. And you take Fourier transform of each residual, and you can take a mean. And you see that this particular shot, you see 2 frequencies, but the mean of all of this averages out to this broad profile, and you have this single peak here. And you can move between your quasi-condensate and your BEC and investigate what happens to this correlation function, the power spectral density. You want to look at that a bit more. The 2 references here where these plots are calculated from theoretical things. And just
sorry, just to be sure, you just to clarify for the audience, you do the Fourier transform and you average, or you average the modulus square of the Fourier transform of the residual?
so we take the Fourier transform, and then you take the modulus squared to get rid of the imaginary part.
Yeah, so this is really an expectation value of the modulus square of the Fourier transform, as is written in the formula below. And this quantity is related to the Fourier transform of the density correlation.
Yeah.
Yeah. And also the temperature again is nano Kelvin, no? Not
yeah.
me.
I put microkelvin on here, and it should be nanokelvin.
We are well below in this experiment.
Yeah, 1,000 times
below 1 micro Kelvin.
Yeah, sorry about that. Yeah. So these things should contain the same information about the spacing of the fringes, or i.e. the spatial frequency. So I don't know if to show this first. Okay, I'll go here. And this is data that we've collected from BC and what are called quasi-condensate and quasi-1D. And I call it quasi-1D because we have mu of the H bar omega perp is less than 1. But so it's chemically 1D, but thermally it's not. It's KT over H bar omega perp is 1 and a bit. And the quasi-condensate, because we don't have long range order anymore, but we are not chemically or thermally 1D, yet we still see these phase fluctuations, which is interesting. So there's no sharp transition between, like I was saying before, a BC and a quasi-condensate to quasi-1D. So it can be, for us, we're investigating this crossover. It's interesting to see how it goes. And we can look at our G2 again to get some of the information, telling you you're more or less likely to find an atom at a certain distance. And you can see that the BC one, it tells you there's no fringes. It's very close to 1 in comparison. Yeah, so this is from Imam Bekov paper, which predicts what the power spectra and G2 should be for a 1D homogeneous gas. And I just thought it'd be interesting to note is one of the limitations of the experiment, which I said before, was the finite resolution. You can see in the theoretical plots here, he has much high frequency peaks in the power spectrum, and that corresponds to distances that are what do we call it, smaller than our optical resolution, and we lose these peaks, so that you can only investigate part of it, and something to be aware of if, when you're considering what kind of things you want to investigate. So now, if we've got time, we can try making some traps if anyone is interested in doing so. So I've got our experiment running live, and it's making BCs at the moment, and the initial parameters are this. And so if someone wants to, let's show it first. Sorry.
So I would start from the more one-dimensional and then go to the, let's say, a more three-dimensional.
Okay. So this is a quasi-condensate. It's not quasi-1D. So if someone wants to suggest a way to make it more 3D, please shout out. If I show you this is the parameters you can choose from.
Rob, you have to do share screen because we see your face.
Oh. All right, sorry. When did I stop sharing the screen? Oh, sorry. Okay. Yeah. Yeah. Okay. So this is running live at the moment. We have a cycle time of about 15.
Sorry, just for a poor theoretician like me. So now you are at home.
I am, yes.
You are at home and you send this parameter to the lab setup.
Yeah. Yeah.
And
So running it remotely.
in this condensing in this moment now in your
It
lab.
is, yeah. Every
Okay.
15 seconds we get a new one. So if someone wants to try and make one which has got less fringes, maybe you can have a think to what parameter I need to change to make it less fringy, which is so less phase fluctuating is what I mean by that.
Sorry, let me understand. So N thermal is order of NBC.
Yeah, so that means that the constant fraction is 50%, and I think T, if you go with T over TC, is probably 0.8 or something like that.
Okay, and how much is the lambda here?
Lambda is about 60.
60.
Yeah.
So in principle it should be well one-dimensional.
But you have a high atom number here, which means that the chemical potential is still high compared to H bar omega perp.
Yeah, so let me explain a bit more. You said, but let me repeat. Come back to the experiment.
Yeah, okay.
So lambda is omega perp divided by omega y is 60, so it's big.
Yeah.
But since the number of particles in this particular experiment is pretty large, the chemical potential is so larger with that we are far from the one-dimensional regime, and we see similar to BC despite lambda being 60. So it's a cigar, but it's not a 1D cigar.
Yeah, well, I mean, you see properties that are closer to a quasi 1D, and well, in terms of the phase fluctuations.
How much is omega mu over omega perp?
It's about 3 or
3.
Yeah.
So despite being so large, you see pretty well the fringes.
Yeah.
Okay. So now can you increase the number of particles in order to destroy the fringes, to let them...
So no, actually the atom number is harder to control. That depends. You can make it smaller, but
Okay,
the other parameters you can change are...
No,
so
but sorry, before that you go on, in order that all the students are following. So what you expect when, not you, to the people in the audience, to the students, what do you expect if you decrease N, that you have more fringes or less fringes? So now I really request to the students of the course so you understand the lambda is pretty large, but now Rob wanted to decrease the number, so the chemical potential. Do you expect more fringes or less fringes?
Are we going to give them a wine point for this?
But in the meantime, do the experiment. So, but I'm asking to students to see if they are somehow...
Okay, I'm going to reduce the atom number now.
Yeah, now you're decreasing N, correct?
And one way we do this is we can deliberately change how long we hold it in the trap for.
I see. So this to decrease N.
Yeah, and this will... so you have background collisions and heating from the chopping potentials that limit how long you can keep things trapped for, because you get atom losses. So by increasing this, I'll lose more atoms. So now we have to wait 15 seconds. Sorry.
So in the meantime, okay, the students can write to me if they expect less fringes or more fringes in this figure when Rob has implemented smaller n.
So now we have about half the original atom number.
Yeah, a lot, because we see that the red is decreasing. So how much number how many particles you have now?
So we have 2.7 times 10 to the 4.
2.7?
10 to the 4. So 27,000.
27,000 particles. Okay. So now now you are producing the time of the figure of the optical density after time of flight for these numbers.
Yeah.
Yeah.
Can I ask a question?
Please, Jerome.
So what are the two curves, the green and red one?
So this is part of the fitting procedure that we have, and so we do the fit to the vertical integration. So you sum all the way down, and you will get this these red lines, and the purple fit to that, and the green is just a horizontal cut through the cloud. So the green would be along this line and this line.
So it's just along the two different axes.
Yeah.
Thank you.
So we can also change the temperature as well. We'll make the cloud longer, shorter, tighter. Anyone have any suggestions what they'd like to try?
Okay, so that what one can expect is that decreasing n, decreasing mu over h omega perp, you have more fringes. And actually, yes, we see less particles, but more fringes with respect to before.
Yeah, I think it's harder to see, but the relative fluctuation compared to the total atom number is high.
Okay, I think it's very clear, very nice. Thanks, Rob. So
Great.
do the students want to explore or propose some other parameter to see the effect?
So the parameters that we can change are the trapping potential, so the longitudinal trapping potential or the radial trapping potential, so omega perp and omega y. Atom number, temperature. Well, yeah, that's it. But
So how do you change temperature?
so the temperature is, we do this radio frequency evaporation, which I didn't explain well, probably, or in much detail, but you basically have you send in RF frequency, which is resonant between the two MF states. Well, so you have so you basically couple +2 to -2, and it goes from a trapped state to an untrapped state, kicks it out, and so you from the higher frequencies you get you're resonant with hotter atoms, and lower frequencies with colder atoms. So as you bring that RF frequency down, you can get a colder cloud.
And in this way, what is the minimum temperature that you can somehow reach?
Well, that's, yeah, dependent on the quality of kind of your experiment. I think lowest temperatures of, it's hard, also it's very hard to measure once you've got no thermal fraction. So there gets to a point where you need to measure it in the temperature with different methods. So once you have more than 80%, then it starts getting tricky. More than 80% condensate atoms.
So I remind you that one would think that decreasing the temperature, you brutally better reach the one-dimensional regime. But I remind you that the condition, yes, so let me say, you have 300 nanokelvin here.
This is looks like it's 200 nanokelvin, 250. Yeah, it's changing.
So when H omega bar is larger than kBt, you are pretty much 1D. So if you decrease the T, you go toward the one dimension. Yes.
Yeah.
Can you show just as a last
how cold to go? Yeah.
The last thing that decreasing temperature, you are more 1D, so you have more fringes.
So that's you increase the phase coherence length if you decrease the temperature. So you actually suppress the fringes, so you make it less fringy, but you are also approaching a more 1D situation, which is interesting. So
show us the experiment somehow so that we understand better.
So I'm just gonna give us a few more atoms and also reduce the temperature at the same time. Let's just
And can I ask something else about the temperature? So how do you measure it? Do you measure it from the fringes, or do you measure it from the tails, or do you know?
Yes, we measure it from the tails normally, but you can measure it from these the fringes, this density correlations, and one of the references I gave. I think I've gone too far. I've kicked out all the atoms. So yeah, let's go too cold. You have no atoms there. But let's just wait for the next shot. It might be. Yeah. So when I showed you that G2 function, you can fit it to get the phase coherence length out. And the phase coherence length is temperature dependent. So by measuring G2, you can get a temperature out, which is useful for when you don't have any thermal atoms, because you can't fit the wings. Yeah, so there's a different way of doing it. It's just you can't do a single shot and get a temperature, where if you have thermal fraction, then you can.
So now he's doing.
Let's hope, anyway.
because before, when you set that parameter was too low somehow.
Yeah, here we go. Okay.
Okay.
So now we have not very many atoms left, but it is colder.
Okay, beautiful. Let's see how much is the temperature that you estimate.
So I think it's 90 nanokelvin.
90 nanokelvin, so very low, because before you had the 400.
Yeah.
But very low number of particles.
It's also less accurate when you have when you have this very small thermal fraction. So yeah, it's a rough estimate.
Very, very beautiful. Thanks, Rob. I don't know, Jacopo, I think we are finishing the hour.
Yes, we are running out of time.
Yeah,
Yes.
so I really want to thank Rob and Tom and Peter for showing us this beautiful picture. And okay, if there are questions, let's do now or after the break, especially if you have a question for Rob.
Sorry, could you explain why making it colder meant there were fewer atoms in the trap? Maybe I missed that.
So that is to do with how it's basically the RF cooling is you call forced evaporation. So you kick out the hot atoms, and then you let the rest of the atoms, they collide with each other and rethermalize to a colder temperature.
Oh, okay.
Look at your Maxwell-Boltzmann curve. You kind of cut off the...
Right, okay, yeah, that makes sense.
And then so obviously when you go colder, you cut deeper into it and you have less acting plane.
Yeah, okay, thanks.
Okay, thanks. Other question for the moment?
Well, so maybe I can ask one. So, so what are you actually doing? I mean, what effects are you trying to probe with that experiment? I mean, surely you don't spend your days looking at snapshots of small clouds increasing and decreasing temperature.
Yeah, so we're investigating this crossover regime between the quasi 1D clouds and the VECs, and there's the power spectrum and the G2 that I showed they have theoretical predictions in 1D, but not in 3D. But we also know that these phase fluctuations should go away. So we're trying to investigate how that happens. And like how deep does the 1D theory still work as we approach what we call the 3D or the VEC regime. Yeah, we're looking at that power spectrum in the G2. What I showed you is what we're looking for.
Okay, thanks.
Okay, Jacopo, so then let's stop, I don't know, a few minutes and then we restart.
Yeah, we can stop about 10 minutes, maybe, no? So
okay.
at 4:20.
At 4:20 we reconvene. Thank you.
Thank you. So thank you for the lecture and the nice experiment also.
Thanks, Rob.
Bye now.